Hello everyone and welcome back to this next lecture. So in the previous lecture we had simulated this buck converter and we had observed the results. Now at this point of time I would say that if any of this was too fast for you or too advanced for you, then my suggestion again, as I say, take a pause from this course. Either go over to the YouTube channels of Corvo, check out their videos on how to use QSpice, or I would say if you want to know about how to use QSpice specifically for power converters, I have another course on simulating DC to DC converters with QSpice where I describe how to use QSpice and how to use QSpice to simulate DC to DC converters. My suggestion, go ahead and take that course because that is a much better introductory course to how to use QSpice for power electronics. Now, I am assuming, however, that if you're continuing, you know how to use QSpice, you're comfortable with this simulation, and you got exactly the same results I did. So with that said, let me come over here and let's start doing a little bit of analysis of the result. So first what I'll do is, let me change this from 0.5 to let's say 0.7. That is, I am now moving my duty ratio up closer to 1 rather than having it at 0.5. So with this, let me just save it and let me run the simulation. And let's go have a look at the result. And you will see that the output voltage has changed. The output voltage is now greater than it was before, and this is simply because the duty ratio has changed. So let's take a look here and you will see that, as you can see, because we have increased the duty ratio, the pulse width has now increased. Rather, the width of the positive pulse has increased and the width of the negative pulse has decreased. Now if we go and have a zoom in on this, you will find that the total time period still remains the same. So for example, if we take a look at the difference between the rising edge and this rising edge, this is one complete cycle. And if you take a look, the difference between these two is 0.1 milliseconds. And that means that this is exactly what we expect. That is, this is a 10 kilohertz carrier waveform. So, which means that our gate pulses have a switching frequency, or rather have a frequency equal to the switching frequency we have chosen, which is 10 kilohertz. By changing the duty ratio, we are merely changing the on time of the power device. And we can always go and have a look at it if we decrease it as well. So in this case, I'm going to decrease it to 0.3. And with this, let me run the simulation again. And let's just zoom in here. And you'll see now that we have decreased the pulse width. And because the reason is, as the duty ratio has decreased, the intersection between the duty ratio and the carrier signal occurs early on in the switching cycle rather than later on. And the result is, again, if you take a look, we still have exactly 100 microseconds as our switching time period, right? So our switching time period is constant. The only thing that is changing is the on time and the off time. We are directly controlling the on time and the off time is indirectly being controlled. This is what we are achieving using pulse width modulation. And depending on the pulse width modulation, you will see here, let me just zoom in here as well, you will see that the output voltage has now decreased further. And that is because the output voltage is simply the duty ratio multiplied by the input voltage. And with the decreasing duty ratio, our output voltage will also decrease. So this therefore shows the pulse width modulation principle. That is, in this case, we are generating a high frequency gating signal. And this means that we are generating a current with a high frequency ripple. And this high frequency ripple is now being removed, because by the action of this filter. That is, we have at the output this inductor capacitor filter which acts as a low pass filter and removes this switched output voltage. So at this stage, if you were to measure, you will find, and I would leave this to you as an exercise, if you measure the voltage at this particular node, you will see that that is a switched voltage. And this switched voltage is now fed to this low pass filter, and as a result the output voltage is a smooth DC voltage. This is how we are converting a switched voltage to a smooth output voltage. And that is the reason why we have chosen a high frequency. If you choose, and this is something I will leave to you as an exercise, if you choose a lower switching frequency, you will find that for the same filter parameters, your output will now contain greater amount of ripple. So for example, if you take a look here, you will see that the output voltage contains a certain ripple. And this is unavoidable because even though there is a capacitor which by its nature is going to decrease the ripple across its output voltage, there will still be some ripple. It is unavoidable. However, if you were to decrease this switching frequency, then with these same parameters, you will find that your ripple will increase. And vice versa. That is, if you were to increase the switching frequency, you will see that for the same LC or the same inductor and capacitor, you will find that your ripple decreases. So this is how we are using PWM, that is by comparing our duty ratio with a high frequency carrier waveform and generating this high frequency gating signals. We are able to filter it with much greater ease in order to produce a smooth output voltage. This is the essential concept of any power electronic converter, which I will continue to emphasize throughout this course. That is, because of using nonlinear elements, we are using a MOSFET. This MOSFET can only operate in two conditions, the cutoff region and the saturation region. That is, either it is conducting and it is a negligible resistance, or it is not conducting and it is an infinite resistance, or a very large resistance which is as good as infinite. And that is why the voltage at this point will be a switched voltage, which means you can never produce just with your power electronic device or power device rather exactly the voltage you want. You will only be able to produce a switched voltage which comes close to your output voltage. The rest of it has to be done through the action of filters. And that is where pulse width modulation comes in, by combining your low frequency signal with a high frequency carrier waveform. You can use low components, or rather you can use filter components which are not too bulky in order to remove the switching frequency harmonics and produce your necessary output voltage. So I hope this technique of pulse width modulation was clear to you. My suggestion, go ahead, play around with all these different conditions and observe these phenomena for yourself and become clear with the fact of how power electronic converters work. And in the course of this, or rather as we progress in this course and as we start examining more and more complex power converters, you will find that essentially the philosophy behind power electronics is exactly the same no matter how complex your power converter gets. So, if you have any doubts, or you have any comments, or you have any other questions, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture where we will conclude on this section. Thank you so much for listening and goodbye for now.